Okay, good morning, everyone. So today, let's continue our discussion. In the previous couple lectures, we showed that by just looking at the symmetry and utilizing fundamental principles, we can uniquely write down the structure of the action for E and M fields, and also how E and M fields couples with matter. Okay? And in the previous couple lectures, we focused on the E and M field part and the coupling to the matter part. And we derived the action, and we utilize the equation of motion, and we utilize action to get the equation of motion. And we find that the equation of motion is exactly what we learned in 505. That's Maxwell's equation. Okay, and there's only a couple parameters we need to determine from the experimental side, and the structure of the theory and the structure of the equation of motion actually has been uniquely determined by symmetry. And experimentally, we only need to measure basically two free parameters, epsilon 0 and mu 0. Then we know everything about the ENM, the dynamics of ENM. Okay, so in the previous couple lectures, we mostly focus on the ENM part and the coupling part to the matter. Okay, but we dropped the action of the matter part in the previous section. Okay, so in the next section, what we are going to look at is the interaction and also coupling between electric field, magnetic field, and the matter. Okay, because we need to look at the matter. So in this section, we will add back our matter parts of the action. And more specifically, for simplicity, we will start from the simple situation. We will consider the matter part, which is 1 point charge. Okay, so we will look at 1 point charge, and this point charge couples with E and M field. What does the equation of motion looks like? As we know early on in the previous part of this semester, we already know if we have a point charge, what will happen. Okay? If we have a point charge and it's moving in the E and M field, then this point charge will feel a force. This force contains two parts. One part is charge times electric field. That's electric force. Okay? And the second part of the force is the Lorentz force. It's a velocity cross product with magnetic field. This magnetic field gives a force to this particle. And this is a force to the particle. And once we have the force to the particle, as we learned in early parts, we can use Newton's second law. But here, the Newton's second law, we need to modify it a little bit. We need to change the mass from a constant to a quantity that depends on velocity. Okay? So mass is our mass is now depends on velocity. It's rest mass times the gamma factor, as we learned. Okay? So we already know the answer. Okay? So in this section, again, we will pretend that we don't know anything about the force or the dynamics how a charged particle moves in electric and magnetic field. And we will pretend that we don't know Einstein's energy equals mc squared, this prediction either. Okay? Again, we will just start from symmetry and try to derive what is the possible equation of motion and what is the possible dynamics a point charge could have. And as we will show later in this section, okay, again, even if we don't know anything about force and Einstein's prediction, by just looking at the symmetry, we can get to the correct equation of motion and Einstein's prediction of E equals mc squared. Everything just naturally follow by just considering the symmetry. Okay? So that's the main task that we are going to work on in this section. Okay, so as I mentioned earlier, in this section, we'll look at a point charge. Okay. And the action of, more precisely, this is Lagrangian. We know that the Lagrangian is actually the spatial integral, space integral of Lagrangian density. Okay, and our Lagrangian density, as we mentioned earlier on, contains three parts. One part is the E and M field part. This part is what we learned earlier on: E squared minus B squared with some coefficients, E squared. Okay, and it has a coupling part that tells us how the electric field, magnetic field, and the matter couples together. And as we have learned early on, the coupling is look like this: scalar potential times charge density and vector potential dot product with a charge current density, and there's a minus sign in between. Okay, so this is the coupling term. And in addition, today we will add one more term to the action. That's a matter part. Okay. And this matter part describes the physics law, the dynamics of a charged point particle, point charge. Okay. So first of all, the first two terms we already know. So the first task we will need to deal with here is to figure out what is a proper Lagrangian for the matter field. Okay, so we figure out the matter field Lagrangian. And before we write down the field, sorry, the Lagrangian for the matter part. Before we write down the Lagrangian for the matter part, let me first discuss a little bit about symmetry, about Lagrangian density, action, etc. Okay, we know that we have been using this Lagrangian density a lot in the previous section. We know that we can define Lagrangian density. This Lagrangian density is defined at each point in our space, each space-time point in our space. Okay, and then if we do a spatial interval of Lagrangian density, we get the total Lagrangian of my system. Okay? And after we do the spatial interval, get the total Lagrangian, we need to do another time interval. And after we do another time interval, we get action. Okay? As we mentioned early on in the earlier parts, action must be a scalar. Okay? Action cannot change under Lorentz boost. And the reason is because we know equation of motion cannot change under Lorentz boost. Okay? All different reference frames should see the same equation of motion. If the equation of motion do not change under Lorentz boost, and we also know equation of motion comes from action, comes from the variation principle of action. So action must also stay the same under Lorentz boost. So we have mentioned early on, we have known from earlier lectures, this action must be a scalar. Okay? If we know that the action is a scalar, then immediately we know that the Lagrangian density is also a scalar. Okay? This is because, as one fundamental principle we discussed in the earlier part of this semester, if we have any equation in physics, okay, any equation for physical observables, if left-hand side is scalar, the right-hand side also need to be a scalar. Okay? We need to make sure that all physics laws in physics are scalar equals scalar, vector equals vector, tensor equals tensor, etc. This structure. Okay? So if we know action is a scalar, then we know immediately the other side is also a scalar. Okay? The other side contains two parts. The first part is a space-time interval. And the second part is this Lagrangian density. This space-time interval is a scalar. Okay? So to see that, we just need to think about the Lorentz boost. Under Lorentz boost, we know that time, we will have time dilation. Okay? Time will increase with a factor of gamma. But at the same time, space, dx, will contract. This is a length contraction. It will shrink with a factor of gamma. This dilation and this contraction both have gamma factor, but one is multiplied by gamma, the other is divided by gamma. One is getting larger, another is getting smaller. So at the end of the day, this multiplication stays invariant. Okay? And for Lorentz boost along the x-axis, y and z don't change. So dy, dz don't change. And dx, dt change, both of them change, but they cancel each other. So this 4D volume interval, dx, dy, dz, dt is a scalar. Okay? If this guy is a scalar, S is a scalar, then we have no other choice. L must also be a scalar to make sure that we have scalar equals scalar in this structure. So the bottom line, Lagrangian density and action, these two quantities are both scalars. Okay, so that's very important. Lagrangian density and action are both scalars. Okay. And this is actually exactly the principle we utilized early on to know that this Lagrangian density need to take this e squared minus b squared form, because we want this Lagrangian density to be a scalar. And e squared minus b squared is a scalar. Okay, that's something we already know. Okay, so once we understand that action and Lagrangian density are both scalars, then immediately we can will realize that Lagrangian is not a scalar. Okay, to understand the Lagrangian is not scalar, we just need to look at the definition. Lagrangian is a spatial integral of Lagrangian density. Okay, we know Lagrangian density is a scalar. Lagrangian density doesn't change under Lorentz boost. But dx, dy, dz is not a scalar. dx, dy, dz is a volume, 3D volume of area. And the 3D volume of area is not an invariant quantity under Lorentz boost. Under Lorentz boost, one direction of my space will contract. That's the direction of my velocity will contract. And that contraction means the volume of this area changes if you do Lorentz boost. Okay, so this dx, dy, dz is not a scalar. L is a scalar, it's multiplying something is not a scalar, so the whole thing cannot be a scalar. Lagrangian density is not a scalar. Okay, this can also be seen. We can get the same conclusion. Lagrangian density is a scalar, but Lagrangian is not a scalar. Okay, And this conclusion that Lagrangian is not a scalar can also be obtained by looking at this relation. Okay? We know that if we have Lagrangian, then we do a time interval for the Lagrangian, then we get action. Okay? That's a definition of action, a definition of Lagrangian relation between Lagrangian and action. We know that action is a scalar. Okay? If action is a scalar, we also know that dt is not a scalar. Time is not a scalar. Time is one component in the four-dimensional coordinate vector. Okay? So time is one component of a 4D vector. It's not a scalar. If time is not a scalar, S is a scalar, then L cannot be a scalar. Okay? This side is not, this side, this left side is a scalar. So right side must be a scalar. Okay? If the right side is a scalar, then we know that dt times L should stay invariant. But dt is not invariant under Lorentz boost. So L cannot be invariant either. Okay? So this is another way to understand that Lagrangian is not a scalar. Lagrangian density is, action is, but the Lagrangian is not a scalar. Okay? Anyway, the bottom line is Lagrangian L is not a scalar. Okay? Now, can we get something like Lagrangian, but it's a scalar? Well, it turns out that's very easy. Okay? We know that action is time integral of Lagrangian. Okay? Let's rewrite this time as proper time. We know dt is d tau times gamma. The time integral is proper time integral multiplied by gamma. This gamma factor is a gamma factor in Lorentz boost, the velocity of the particle, as we already learned earlier. Okay, and we know that time interval is a proper time times the gamma factor. Gamma factor is 1 over square root 1 minus v square over c square, and the velocity is the velocity of one particle. Okay. We know that proper time is a scalar. Okay, if action is a scalar, proper time is also a scalar, then this gamma times L must be a scalar. Okay, we know Lagrangian is not a scalar, but gamma times Lagrangian for point particle must be a scalar. Gamma times Lagrangian is scalar. Okay, Lagrangian is not a scalar, but gamma times Lagrangian is. This is because scalar must equal to a scalar. If S is a scalar, this whole thing must be a scalar. And the d tau mass is a scalar. We already know proper time is a scalar. So gamma L, gamma times Lagrangian, must be a scalar. Okay, so that's a very important principle. Gamma times Lagrangian must be a scalar. Okay, so now let's look at the coupling part first. Okay, so for the coupling part, we already know that the coupling between E and M field and the matter is this guy. Okay, scalar potential times charge density minus charge current density dot product with vector potential. Okay, and with a minus or a sign in front. So this is a Lagrangian density, and if we want a Lagrangian, we do a dx dy dz integral. Okay, so dx dy dz integral is a volume integral of Lagrangian density is my Lagrangian. Okay, I'm looking at the Lagrangian here. So this is Lagrangian for the coupling part. Okay, so for the middle part. Okay, so then let's look at this coupling part. Okay, so for a point charge, in this section we'll consider point charge. Okay, for a point charge, the charge density is a delta function. Okay, it's a delta function Q. Q is the charge of my particle times delta function R minus R0. R0 is the location of this point charge. Okay, so this point charge is say is at R0, then the charge distribution is this delta function. Okay, and similarly, current density of a point charge is this guy. Again, it's a delta function. It tells me only at the location of my point charge, I have current. Away from this point, there's no current. I only have point charge. Okay, and the current is proportional to the charge, also proportional to the velocity of the particle. If the particle is moving faster, this current should be stronger. Okay, so the current density for a point charge is this guy. We know the charge density, which is this delta function. We know the current density, which is this delta function. So we plug in the charge density and current density into my Lagrangian. Then I get the Lagrangian for a point charge. More precisely, the coupling part of the Lagrangian for a point charge. Okay, and this guy, this is what we have. Okay, So we can put the common factor Q out. We can put the common factor delta function out. And in the middle, we have scalar potential minus velocity dot vector potential. Okay. And we have a 3D integral. Okay. 3D integral of a delta function is really easy. The 3D integral of a delta function is just, we replace all the r by r0. That's it. Okay. So I have Q, the minus sign is from the definition of the minus sign, Q times phi, Q times phi. Okay. And this phi is a scalar potential at r0. R0 is the location of my charge, and this comes from the delta function. Okay. Similarly, for the other term, we have minus sign in front and minus sign here. So the two minus sign cancel, so we get a plus sign. We have charge Q times velocity times vector potential A. Q times velocity dot product is vector potential A. And again, this vector potential is a vector potential at R0. R0 is the location of my point charge. Okay. So the coupling term, the Lagrangian for the coupling term between field and my point charge is this guy. Okay. Charge times scalar potential with a minus sign plus charge times velocity dot vector potential at the point, at the location of my point charge. Okay, so this is my Lagrangian for the coupling part. We just mentioned in the previous sector, Lagrangian is not a scalar, but Lagrangian times gamma should be a scalar. Let's check whether this is true. Okay, we know my Lagrangian here for my point charge, and then I multiply gamma in front of it. This gamma is a gamma factor 1 over square root 1 minus velocity over speed of light square. Okay, so we multiply gamma for my Lagrangian. It's the same two terms, but I got the gamma factor here and the gamma factor here. Okay, I want to argue that this guy is a 4D scalar. Okay, and this guy indeed is a 4D scalar. We can prove that very easily. To show that, let me remind you the definition of two 4D vectors. Okay, so in the earlier chapter, we defined the 4D velocity, four-dimensional velocity. Okay. The four-dimensional velocity, the first component or the zeros component is speed of light times gamma. Okay, and the rest of three components is velocity x, velocity y, velocity z times gamma. That's the definition of the 4D velocity. Okay. And in earlier chapters, we also defined another 4D vector, which is a 4D scalar and vector potential. Okay. You have scalar potential divided by speed of light c and the vector potential x, y, z combined together as a 4D vector. This is another 4D vector we defined earlier. This is a 4D potential, okay. Scalar and vector potential. So these two 4D vectors are what we defined earlier. Okay. If we make a inner product between these two 4D vectors, remember the inner product is one 4D vector times another 4D vector with a matrix tensor in the middle. Matrix tensor is 1 minus 1 minus 1 minus 1. Okay, and when we multiply these two 2D vectors together using this inner product, we get a scalar. Okay, we mentioned earlier, vector inner product with another vector gives me a scalar. This is similar to 3D space, dot product between two vectors gives me a scalar. And in 4D space, this is a dot product. This is inner product. The inner product in the matrix tensor. Okay. After we do this inner product, we get a scalar, and then we multiply this scalar with a prefactor minus q. In one of our homework, we proved that q, charge, is a scalar. So charge density is not a scalar, but the charge is a scalar. Okay. We proved this in one of our homework problem. So charge is a scalar, inner product is scalar, scalar times scalar is still a scalar, so this whole thing must be a scalar. Okay, so indeed we proved that gamma times Lagrangian is a scalar. Okay. So for the coupling parts, we know exactly what the coupling parts of a Lagrangian looks like, and we verified that by multiplying a gamma, this guy is a scalar. Okay, now let's look at the Lagrangian for the point charge. Okay, so we know the Lagrangian for the coupling part already. Lagrangian for the E and M part, we also know it already from previous lectures. It's this guy, E squared minus B squared with a volume integral. Okay, and the only part we don't know yet is the Lagrangian for my matter, for my point charge. What is the Lagrangian for my point charge? Well, here we to get the Lagrangian for a point charge, we utilize the fact that gamma times Lagrangian need to be a scalar. Okay, so let me write it down here to highlight it. Okay, so the key principle to get to know what gamma is, what Lagrangian is. So we want to know our Lagrangian for my matter particle, for my point charge. Okay, and to figure out what this Lagrangian is, we utilize the fact that the Lagrangian of my matter field times gamma need to be a scalar. Okay, and this need to be a 4D scalar. This need to be a 4D scalar. And we also know that this Lagrangian point charge, it should contain kinetic energy, but it should not contain potential energy. Okay, so this is a little bit different from classical mechanics. In classical mechanics, we know that Lagrangian contains two parts: kinetic energy minus potential energy. Okay, but here I want to argue the Lagrangian only contains kinetic energy. There is no potential energy here for the matter part. Okay, the reason we don't need potential parts here is because we are doing E and M. Okay, when we are doing E and M, the potential energy part is here in the coupling. Okay, the potential energy for point charge comes from the potential energy of the E and M field. Okay, the potential energy is already included in the coupling term when I couple my matter field with an E and M field. Okay, so here I assume there is no gravity. Okay, we don't handle gravity here in special relativity. We know special relativity do not include gravity. If you want gravity and gravity potential, you need to go to GR, general relativity. Okay, if we ignore gravity potential, then the potential, what we call the potential in classical mechanics is actually the E and M field potential. And the E and M field potential is in the coupling term. It's not in the matter part. Okay? The matter part should only contain kinetic energy. Okay? So that's the two principles we should use. The first principle is that gamma times my Lagrangian should be a scalar. And the second principle is my Lagrangian of my matter part, it should only contain the kinetic energy part. Okay? Because it only contains the kinetic energy, it should only depend on the velocity. It does not depend on the position. Position doesn't matter. It only depends on the velocity of my particle. Okay? And so in other words, we have gamma times L matter. Okay? This whole thing needs to be a scalar. And it needs to be a function of velocity. In other words, we need to utilize velocity to make a function of velocity, which is a scalar. Okay? How can we make a scalar out of velocity? There's only one way to do that. Okay? We know velocity is part of a 4D velocity vector. Okay? So the velocity vector, 4D velocity vector, we just defined here. The first component is gamma times speed of light. The rest three components are Vx, Vy, Vz times gamma. Okay? So velocity is actually a 4D vector. If we have 4D vector, we want to use this 4D vector to build a scalar. There's only one way to build a scalar. Okay? That is to do the inner product of my velocity to itself. Okay? We have a vector, only one vector. We want to build a scalar out of this vector. There's no other way. We must do the inner product. That's the only way to get the scalar. Okay? And if we do the inner product for this velocity, we already did this calculation early on. And here is some details you can follow. Okay? Just by definition, when we calculate this inner product, it's this guy. And after we cancel all the common factors for the numerator and denominator, this inner product is speed of light squared. Okay? There's only one scalar we can build. That's this one. And this one is a constant. Okay? In other words, this gamma times L matter must be a constant. Okay? Because we need to use velocity, and we need to use velocity to build some scalars, and the only scalars velocity can build is speed of light constant. Okay? So from this observation, we immediately come to the conclusion: gamma times Lagrangian of matter must be a constant. Okay? The value of this constant we don't know. We will need experiment to determine this value, but we know it's a constant. Okay? So it turns out that this constant happens to be negative, and we can show that if it's positive, then the system will lose its stability. Okay, but it has to be negative to maintain stability. Okay, because this constant is negative, I will call this constant minus alpha. So alpha is a positive value. Okay, so the bottom line, gamma times L matter need to be a scalar, and the only scalar we can have here is constant. Okay, it cannot vary with time, and cannot vary with x, y, z, or t. It must be a constant, and it must be a fundamental constant. Okay, and this constant we don't know its value yet, so I will call it minus alpha. Okay, so in other words, gamma times my Lagrangian is minus alpha, which means my Lagrangian is minus alpha over gamma. I divide gamma to the other side. Okay, and gamma is 1 over gamma is just this square root of 1 minus velocity over c squared. This must be the Lagrangian of a point charge. So point charge, there's no option. By just looking at the symmetry, symmetry here means everything should be invariant under Lorentz boost. We immediately come to the conclusion this Lagrangian have to take this form. We don't know yet what is the value of alpha, which need experimental measure, but we know there is a constant here, alpha. And up to this constant, the Lagrangian, we already know what it is. Okay, we will determine this constant alpha slightly later. Okay, it turns out this alpha is an old friend we are very familiar with. This alpha is actually the rest mass times speed of light squared. In other words, this alpha is actually the rest energy of my point charge. Okay, it's the energy of my point particle when it's not moving. It's m0 c squared. And this quantity is a constant. Once I have the particle here, okay, if I have this particle, and I assume there's no nuclear reaction or particle annihilation, if I have this particle, this quantity is a constant. Okay. So for point charge, this quantity alpha, we will show it later, is m0 c squared. Okay, anyway, so for this, at this moment, let me keep this alpha as an unknown parameter. We will show later, it's just rest mass times speed of light squared. Okay, so let me erase everything. Okay. Okay, so this is Lagrangian. So once we learn the Lagrangian, as we learned in classical mechanics, we can define the so-called canonical momentum. Okay, so the Lagrangian, so the momentum is Lagrangian. We do a variation of Lagrangian to velocity. Okay, so we do a derivative of Lagrangian to velocity, and we can do this derivative for velocity along x, y, or z. That gives me momentum x, y, and z. Okay, so it's a variation of L to dr dt, or a variation of L to v, the I component, the i's component of velocity. Okay, and Lagrangian we know it's minus alpha times this guy. Okay, and the velocity is here. We just need to do a variation of this function of delta v. Okay, and this is just a derivative, a standard derivative. Okay? And the top part is delta square root 1 minus vx squared over c squared minus vy squared over c squared minus vz squared over c squared. Okay, I'm just rewriting this v squared as vx squared plus vy squared plus vz squared. And then we do a partial derivative of, say, vx. Then I get the momentum of x. If we do the derivative of vy, we get the momentum of along y direction. If I do the derivative for vz, we got the momentum along the z direction. Okay? And this variation is a standard, first order derivative for square root function. And if we go through this calculation, this is what we get. Okay? So this momentum along the i's direction, this I can be x, y, or z, is alpha, the same constant we have here, okay, divided by speed of light squared times gamma, the same gamma factor we have here, okay, multiplied by velocity along this direction, okay, along the same direction. Okay, and remember, we learned early on momentum for a point charge, for a point particle in relativistic physics is mass of this particle times velocity. Okay, and the mass is rest mass times gamma. Okay. In other words, momentum is rest mass times gamma times vi times velocity. Okay. If we compare this conclusion with what we find here, we see vi, we see gamma, which means this alpha over c squared, this constant, alpha over c squared is a constant. This constant must be the rest mass of my particle. Okay, so this constant is a constant. We just call this constant the rest mass of my particle. I call this constant the rest mass of my particle. Then I recover the definition of momentum we learned earlier. Rest mass times gamma times velocity. Okay, so that's the momentum. Once we know the momentum, we can immediately get the Hamiltonian, or the energy of my particle. What is the energy of my particle? Okay. The Hamiltonian, we get the Hamiltonian through the Lorentz transformation, same as what we learned in classical mechanics. Okay. So for each momentum, we multiply the corresponding velocity. So for px, I multiply vx, py, I multiply vy, pz, I multiply vz. Okay. Then I minus the Lagrangian. Add these three together, minus Lagrangian. Okay. For momentum, we already showed the definition here. Okay, we already know what momentum is, px, py, pz. I just plug in px, py, pz using this formula and multiply by vx, vy, vz, and this is what we get. Okay, so this is the first three term. And for the last term, minus Lagrangian. Lagrangian is minus alpha gamma. So minus Lagrangian is just alpha over gamma. Alpha over gamma is just this guy. Okay, so this is my Hamiltonian. And we can massage the formula a little bit. Plug in the value of gamma. Gamma is 1 over this square root. So this is gamma. And we have alpha. This is alpha. This whole thing is just v squared. V squared. And we keep the c squared downstairs. Keep c squared downstairs. Okay. So we have these two terms. And we can combine these two terms together. If we combine these two terms together with some quite straightforward algebra, we find that the Hamiltonian is this guy. Okay. Hamiltonian is this guy. Again, we find that the energy, Hamiltonian, by the way, is energy. Okay, we find that the energy of my point charge depends on velocity in this way. The energy of my point charge, let me write something. We find that Hamiltonian is energy of my point charge is proportional to some constant divided by square root 1 minus v squared c squared. Okay, so I find that my energy is proportional to gamma. And we can ask the question, what is the energy when my particle is not moving? Okay, what is the energy when my particle is not moving? When my particle is not moving, velocity is 0, the denominator is 1, so it's alpha. So from the definition of Hamiltonian, we immediately realize that if the particle is not moving, its energy should be alpha. In other words, this alpha is the energy of my particle when it's not moving. Okay. And early on in the definition of momentum, we showed that this alpha over c squared is what we call the rest mass. In other words, this alpha, this alpha is just the rest mass times c squared. Okay, so we immediately realize that the energy of my particle when it's not moving is rest mass times speed of light squared. And when it's moving, it's rest mass times speed of light squared times gamma. Okay, and the rest mass times gamma times speed of light squared, rest mass times gamma is m. So that's E equals to mc squared. Okay, so notice that in this derivation, we didn't assume anything. The only thing we assume is that the Lagrangian times gamma is a scalar. And if Lagrangian times gamma is a scalar, then the Lagrangian have to take this form. Then we have to find that momentum is proportional to velocity times gamma. Okay, and the energy is proportional to some constant times gamma. Okay, and more precisely, energy is some number times gamma, and momentum is some number. Is some number times velocity times gamma. Okay, and these two numbers are related with each other. Okay, so these two numbers are related with each other, and the ratio between them is c squared. Okay, And if we call this one m0, if we give it a name m0, then we immediately realize that the coefficient that should be utilized here is m0 c squared gamma. Okay, so the only physical parameter we need to measure here is m0. We need to measure experimentally this quantity, and once we get this quantity, everything is known. Okay, the energy is the same coefficient times speed of light squared times gamma. The momentum is this m0 times velocity times gamma. All the physics we learned early on get recovered. Okay, so that's the energy and the momentum of the particle. Okay, so we have the Lagrangian. We have the Lagrangian for the matter field, and we also have the Lagrangian for the coupling. So Lagrangian for the matter field is my minus alpha constant times divided by gamma, and alpha constant we already know that it's rest mass times beta light squared. Okay, and the coupling part, as we showed early on, is charge times scalar potential plus charge times velocity dot the vector potential. This is the Lagrangian of my matter field, and the Lagrangian of matter field coupled to the E and M fields. Okay, so now let's try to find the equation of motion. Okay, so in order to find the equation of motion, we perform the standard variation calculation. Okay, the same as what we learned in classical mechanics. So before we find the equation of motion, so let's first do one thing. Okay, let's first find the momentum of these particles. Okay, so early on we already showed the momentum of these particles using this definition of momentum. Okay, but there is a small problem. When we write down this definition, okay, we are writing only the Lagrangian of the matter field. We didn't include the Lagrangian of the coupling. Okay, if we have, in reality, my Lagrangian actually contains both matter field and the coupling. Okay, and it also contains the E and M part. Okay, so in order to define the momentum of my particle, I should do the Lagrangian derivative of velocity. Okay, this Lagrangian should be the Lagrangian of everything. Okay, so in this section, we only calculate the Lagrangian. We only include the Lagrangian of the matter. We didn't include the Lagrangian of the coupling and the Lagrangian of the E and M part. Okay, so in the next section, we will redo the definition of momentum, including both matter parts and the coupling parts and the E and M part. Okay, so the E and M part is fine. The E and M part we can throw it away because the E and M part do not contain the velocity of the particle. Okay, the E and M part of the Lagrangian is this guy, is E squared minus B squared. The E and M part don't contain the velocity of the particle. So E and M part don't contain velocity, so we don't need that part when we do the variation calculation. Okay, but we do need the coupling part because the coupling parts do contain velocity. Okay, so matter field part contains velocity, we already know. The coupling part, if the particle is charged, the particle has charge, the coupling to the E and M field also contains velocity. Okay, this means if this particle is charged, its definition of momentum should be modified by the coupling to the E and M field. And this is something we're going to study in this section. Okay, so in this section, we replace our Lagrangian by this complete Lagrangian. In principle, we should also add the E and M field. The E and M field, we don't really need it here because the E and M field don't contain velocity, so they don't contribute to momentum for the momentum of the charged particle. Okay, so here we include the matter part and the coupling parts, and we calculate the momentum for the charged particle. Okay, again, we are using the standard definition, variation of Lagrangian to velocity x gives me momentum x, variation of Lagrangian to velocity y gives me my momentum y, variation to velocity z gives me my momentum z. Okay, and again, I can split this Lagrangian into two terms. One is the matter part, the same as what we did before in the previous page, and the second part is the coupling part. Okay, the matter part of the variation is the same as what we had before, and we get the momentum of point particle as we learned before. Rest mass times gamma, which is the mass of my particle, and the velocity v times velocity. Mass times velocity is the momentum of my point particle. Okay, but the coupling term, as I mentioned earlier on, it also depends on v. So when we try to do a variation of v, this coupling term also gives me a contribution. And this contribution is q times ax. Okay? If we do the variation here, it's very straightforward to show that Q survives and the Vx and Ax multiply together. So if we do a derivative of Vx, we get Ax. Okay. Similarly, for the y direction, for the momentum along y, the coupling to the E and M field gives you one additional term. That's QAy. Okay. For momentum along the z direction, the coupling to the E and M field gives you additional term, AQZ. Okay. The bottom line, if the particle is not charged, the momentum is here, what we give you earlier. Okay, it's a mass, less mass times gamma times velocity. But if the particle is charged, the Lagrangian contains one more term. That's the charged particle couples to the E and M field. That term will give you additional contribution for your momentum. That additional contribution is charge of this particle Q times the vector potential A. Okay, so if we write this whole thing in a vector formalism, we find that for a charged particle, its momentum is capital P. Okay, and this capital P contains two parts. One part is this lowercase p. Lowercase p is our old friend, gamma rest mass times velocity, or mass times velocity. Gamma times m0 is mass. Okay, but it also has additional term, which is QA, where Q is the charge of my point particle, and A is the vector potential. Okay, if my particle is charge neutral, if my particle don't contain charge, Q equals 0, then this second term disappears and recovers what we learned before. But if my particle is charged, the proper definition of momentum is this guy, this whole thing, not just the mass times velocity. Okay, so charged particle and the charge neutral particle have different momentum. Charged particle has one additional momentum coming from charge times the vector potential. Okay, bottom line, the charged particle, the momentum get one additional correction, which is charge of my particle times vector potential. Okay. Okay, now let's, so after we understand the momentum, we can write down our Hamiltonian. Okay, so right now, so this time, when we write down the Hamiltonian, we use the full momentum and the full Lagrangian. Okay, so for the full momentum, we know that for a charged particle, the momentum capital P contains two parts. The regular part, we already know very well, and this new part, Q times vector potential. Okay, that's my capital P. And the momentum times V minus L should give me my energy, my Hamiltonian. Okay, this is my momentum, dot product of V, okay, and then minus Lagrangian. And this minus Lagrangian part again contains both my matter part and the coupling part. Okay, in principle, we can also add the E and M part here. Okay, but that part is the energy. That part will give you energy of the E and M field, not the energy of this particle. Okay, so in this section, we're focused on the energy of this particle. The energy of E and M field we will consider it later in later sections. Okay, so we're not consider the E and M field part. We're only consider the charged particle part. For the charged particle part, this is its Hamiltonian, its energy. Okay, and we can simplify this formula a little bit and massage the formula a little bit. And after some simplification, most of the term cancels out, and eventually we get a very simple form. Okay, the first term is again our old friend, mc squared. That's Einstein's prediction. Okay? The energy of point particle, energy of object, is mass times speed of light squared. But for charged particles, there is one additional term for Hamiltonian. This additional term for the Hamiltonian is charge Q times the vector potential. Okay? So in other words, the E and M field for a charged particle, E and M field will change its momentum. It will also change its energy. It changes momentum by Q times vector potential. It changes its energy by Q times scalar potential. Okay, and this shift in energy is very easy to understand. Okay, what is Q times scalar potential? Q times scalar potential is nothing but electric potential energy. Okay, so that's the definition of electric potential energy. Q times phi, that's electric potential energy. Which means for a charged particle moving in E and M field, the energy is not only the kinetic energy. It also contains the potential energy from electric potential. Okay, so this part is easy to understand. And the momentum part of the modification is a little bit harder to understand. It's a little bit harder to realize. Okay, but momentum part is also get modified, and it's modified by the vector potential. This part is not, it does not have a simple interpretation as a potential energy or something. This part, the modification of momentum, is a relativistic physics. Okay? If we follow the relativistic physics, we will see that momentum tends to get modified. Okay? And for the energy got modified, we don't really need relativistic physics. Even in Newton's mechanics, we can realize that energy should get modified because we have electric potential. But this momentum part is a relativistic effect. It tells us momentum of a charged particle need to be modified by the vector potential. It has to be modified by the vector potential. Okay, now let's look at the Hamiltonian or the energy a little bit more. Okay, we know that the energy, the kinetic energy more precisely, the first term of the energy, if we don't look at the potential, okay, the first term of my energy can be written in terms of mc squared. We can also write it in terms of p squared c squared plus rest mass squared speed of light times to the power 4. Okay, and this p I want to highlight is the small p. The small p is this guy. Okay, so early on when we say energy equals p squared c squared plus m squared c to the 4th, this guy, we are assuming this p is this p. Okay, it's not really the momentum of a charged particle. It's part of the momentum of my charged particle. Okay, if we want to use the momentum of my charged particle, capital P, the energy should look like this. Okay, so for a charged particle, the Hamiltonian contains 2 terms. The second term is charge times scalar potential, our old friend. Okay, the first term is this guy. Okay, this guy is the same as the energy of a charged neutral particle. Okay, and we can write it in this way, but we should use small p, not capital P. And the small p is capital P minus QA. Okay, small p is capital P minus QA, which means I can replace this small p by capital P minus QA. Okay, in other words, for a charged particle, the Hamiltonian or the energy should be written in this way. Okay, it's total momentum, a charged particle total momentum, capital P minus QA squared, c squared, plus rest mass squared, speed of light to the 4th square root. This is the kinetic part of the energy, okay, including the rest mass energy. And then plus the potential energy. Okay. In other words, if we compare the Hamiltonian of a charged neutral particle and a Hamiltonian of a charged particle, we realize that from relativistic physics, we need to do 2 modifications to change a charged neutral particle into a charged particle. The first modification is obvious. The first modification is we need to add an electric potential energy. Okay, so for a charged particle, we need to add this term. That's the potential energy. It's from electric potential. And secondly, and more importantly, we also need to modify the momentum. Okay, so for charged neutral particle, energy is momentum squared c squared. But for a charged particle, the energy is not momentum squared c squared, blah, blah. It's momentum minus QA squared times c squared. Okay? So for a charged particle, if we have to start from the Hamiltonian of a charged neutral particle, we start from the Hamiltonian of a charged neutral particle, and we want to write down the Hamiltonian of a charged particle, we need to do 2 things. One is to add electric potential. Oops. And the second is to replace P with P minus QA. Okay. That is what I summarized here. Oops. Let me go down a little bit and summarize. Include this additional potential term and replace P with P minus QA. Okay. And this is called minimum coupling. Okay. You probably have already seen this structure in quantum mechanics. Okay. In quantum mechanics, when we try to write down the Hamiltonian of a charged particle, this is exactly what we do. Okay. So in quantum mechanics, say Schrödinger equation, h bar squared divided by 2m, derivative squared, plus some potential energy. Okay. So if this is a Hamiltonian of a charged neutral particle, Then if I want to write down the Hamiltonian for charged particle, what we should do is the following. We need to do two things. First of all, we need to replace this potential with one additional term, add one additional term. The additional term is the electric potential energy. Okay, that's easy and obvious. And in addition, we need to rewrite this kinetic energy part. Okay, the kinetic, with the minus sign. The kinetic energy part we used to have is 1 over 2m p squared, and p is minus I gradient h bar. Okay. So that's my old kinetic energy for charged neutral particle. For a charged particle, I need to replace this minus I h bar gradient momentum by minus R h bar gradient minus QA. Okay, so in the kinetic energy part, I need to replace minus IH bar gradient by this guy. Okay. This is the reason why in quantum mechanics, we do this minimum coupling. We replace the derivative momentum from derivative to this guy to get the Hamiltonian for charged particle. Okay. So of course, in quantum mechanics, most of the time we are dealing with non-relativistic quantum mechanics. Okay. But I want to highlight that this minimum coupling, this principle, you should replace P with P minus QA. This principle comes from relativistic physics. Okay. From relativistic physics, we learned that we have to do this substitution. And then in the non-relativistic limit, although Schrödinger equation describes non-relativistic particles, we still need to do the same transformation. We still need to do the same substitution, same minimum coupling. Okay. So from classical point of view, from non-relativistic physics, from non-relativistic quantum mechanics, it's probably very hard to understand why we need to do this substitution when we try to couple a particle to the E and B field. But if we think about this from the relativistic point of view, this is obvious. This has to be done. Okay? And we can understand this minimum coupling now from relativistic physics, and then take the non-relativistic limit. If we take a non-relativistic limit, we will recover what we learned in quantum mechanics, like the Schrödinger equation. Okay, anyway, this is the bottom line. We learned that from relativistic physics, for a point particle with charge Q, we should replace this momentum by this guy if we want to couple it to an electric and magnetic field. And that is a minimum coupling, the same thing we learned in quantum mechanics. Okay. So one more thing I want to mention about minimum coupling is that this minimum coupling can also be written in terms of in a 4D structure, okay, in a 4D vector structure. As we learned early on, every physics law, we should be able to write it in the scalar vector tensor structure to make sure that it's invariant. All the physics laws are invariant under Lorentz boost. Okay? In different reference frame, we see the same physics law. Okay? So in order to understand the minimum coupling in terms of a 4D representation, we just need to think about a very simple thing. Okay? Let's think about a charged neutral particle first. We know that for a charged neutral particle, we have energy and momentum, and we can combine energy and momentum together to form a 4D vector. This is my energy and momentum vector, as we learned earlier. Okay, and we know that this energy and the momentum 4D vector, we can do an inner product of this 4D vector to itself. Okay, if we have a 4D vector inner product to itself, the inner product of two 4D vector is a scalar, so we get a scalar. And with some straightforward calculation, we can verify this scalar is nothing but rest mass square times speed of light square. Okay, so this is m0 square c square. Okay, and this guy is also, this inner product is also e squared over c squared minus p squared. Okay, and if we use this equation, we can massage this equation a little bit and try to solve for what is the value of energy E, and then we immediately get the dispersion relation for a relativistic particle. E equals to momentum squared c squared plus rest mass squared speed of light to the fourth. Okay, that's we already know earlier. And now let's consider a charged particles. Okay, so for a charged particles, what do we need to do are the two things. One is to change Hamiltonian, change energy. Another is to replace momentum. Okay, these two modifications can be combined together as one 4D vector. Okay, so we know that for a charge neutral particle, my energy and momentum, we should use this 4D vector to describe my energy and momentum. For a charge particle, it turns out that we should use this 4D vector. Okay, this is a 4D vector. We already know energy and momentum is 4D vector. And we also know scalar potential over C and the vector potential gives me a 4D vector. Okay, and Q is a scalar. Scalar times a 4D vector is also a 4D vector. So the second object is also a 4D vector. And these two 4D vector, 4D vector minus another 4D vector is still a 4D vector. Okay, vector plus vector, vector minus vector is still a 4D vector. Okay, so we got this 4D vector. And we can calculate the unit product of this 4D vector. Okay, if we calculate the unit product of this 4D vector, it looks like this. Okay, so this is my 4D vector. And now let's replace the energy. Okay, so there is energy here. Let's replace energy with the proper energy of a charged particle. Okay, if we replace this energy with the proper energy of a charged particle, this inner product, okay, the inner product of this 4D vector to itself, can be rewritten as this. Okay, we can show that this guy equals rest mass squared speed of light squared. Okay, so for charged particle and the charged neutral particle, the difference is here. Okay, so for charged particle, the energy momentum vector inner product to itself gives you rest mass squared speed of light squared. Okay, but for a charged particle, it's this vector inner product to itself equals to rest mass squared c squared. Okay, that's the difference between charged and the charged neutral. So charged neutral particle, in order to get the rest mass and speed of light squared, you do the energy momentum tensor inner product energy momentum tensor. For a charged particle, we do this guy, this 4D vector, inner product to itself. That inner product gives me rest mass squared speed of light squared. Okay. So in other words, if we want to start from a charged particles, if we want to start from charged neutral particles and go to a charged particle, okay, the only thing we need to do is to replace the 4D energy momentum tensor with this new 4D, to replace this energy momentum 4D vector with this new 4D vector. Okay. So for charged neutral particle, the energy and the momentum 4D vector looks like this. And for a charged particle, we should use this vector to replace the energy and the momentum vector. Okay. And the inner product of this vector to itself is m0 squared c squared. This is the minimum coupling in 4D formalism. And this 4D formalism guarantees us this minimum coupling stays invariant under Lorentz boost. Okay? If this minimum coupling we write down in one reference frame, in another reference frame, it will look exactly the same. Okay, so that's all about minimum coupling. So after we understand this minimum coupling, now let's go to the real task of this chapter, this section. That's to figure out the equation of motion. Okay, so we know the Lagrangian of the matter field, we know the Lagrangian of the coupling parts, and we can write them together. This is my Lagrangian. Okay? And the only thing we need to do here is to, once we have a Lagrangian, we can immediately write down the equation of motion, which is just this guy. Okay? So this is the same equation of motion we learned in classical mechanics. So on the left-hand side, we have variation of Lagrangian to velocity, then do a time derivative. And on the right-hand side, we have Lagrangian variation to coordinates, and they need to equal to each other. So this is equation of motion for Lagrangian. Okay. And Lagrangian we already know, it's this guy. Okay, and we just need to do the variation. Here I want to highlight that in the Lagrangian, we have phi and vector potential A. Okay, this phi and this A, we should take the value at r and t. R and t is a coordinate of my particle. So at time t, my particle is at r. Okay, so this phi and this A, the field value, we should take it at the position of my particle. Same position, same time as my particle. Okay. In other words, this phi term and this A term can tensor r. They can tensor r. That's the reason why it will enter the equation of motion. Okay. By this coupling term will enter the equation of motion. Okay, so let's look at this. Equation of motion. First, let's start from the right-hand side. The right-hand side, first, let's look inside the time derivative. Okay, So inside the time derivative here, we have a variation of Lagrangian to velocity, variation of Lagrangian to velocity. Okay? So what is the variation of Lagrangian to velocity? By definition, this is momentum. Okay, and we showed earlier, variation of Lagrangian to velocity is just momentum of the same direction. And momentum for charged particle, we already know it's a charge neutral part, m0 gamma velocity plus additional contribution, q times a, charge times a. Okay? So this term we already know, we already figured out in the previous section. Okay, so this means that the left-hand side is really easy. The left-hand side is the time derivative of this guy. Okay, so time derivative of this guy is the time derivative of these two objects. I can split it into two terms. The first term is time derivative of small p, and second term is time derivative of vector potential. And small p is my our old friend, US mass gamma times velocity. Okay, so that's in the small p. Okay, so this is left-hand side. Okay, so here we need to spend a little bit of time working on this a part. Okay, so here we want a time derivative of a. Okay, we want to calculate time derivative of a in the equation of motion. What is the time derivative of a? Okay, a is a function of r and t. It depends on the position of my particle. It also depends on time. So this r is the location of my particle time t. Okay, so this r also secretly contains t. Okay, this r is the location of my particle at time t. Okay, so this r is also a function of t. In other words, a contains two parts dependent on t. One is this obvious part. Obviously, the field depends on t. Okay, if they have a variation, if the field actually the value changes, it depends on t. But on top of that, this r, the location of my particle, also depends on t. So more precisely, we should write a in this way. Okay. A is a function of r and t, but r is actually also a function of t. Okay, because r is the location of my particle and time t. As a result, if we want to do the time derivative of a to t, we need to use the chain rule. Okay, the chain rule tells me the time derivative of a to t, one contribution comes from partial derivative of time. That's this time dependence. Okay, but this r also depends on t. So to get that part of dependence, we need to use the chain rule. We first do the derivative of a to r, and then we do the derivative of r to t, multiply them together. Okay, and this r part and this partial t part combined together is my total time derivative of a. Okay, so this time of derivative of a is actually complicated because it contains both obvious t dependence and also a hidden t dependence because r depends on t. Okay, so nevertheless, we can use the chain rule to calculate this, and we have r derivative of a, times dr dt. dr dt is nothing but velocity. So this is r derivative of a times velocity. And second term is time derivative, partial t of a, partial t of a. Okay. So we can rewrite these two terms together in a vector form. It's velocity dot product with derivative. This is 3D dot product acting on ai. That's the first term, plus the partial a, partial t. So dA dt contains those two terms. Okay, so we should plug in this this object into my equation to replace dA dt. Okay. Okay. So for those who are, if you are really interested in the difference between dA dt and the partial a, partial t, here I have some more details explaining the difference. And this small part is optional. If you are interested in that, you can read this part of lecture notes to figure out what is precisely the difference between dA dt and the partial a, partial t. Okay, anyway, so the left-hand side, we know is this guy, and we know dA dt is this guy, so I can replace dA dt with this guy. So the left-hand side becomes this. Okay, so this is my left-hand side on my equation motion. The right-hand side is a variation of L to R. Okay, the variation of L to R, the Lagrangian contains two parts. This part don't contain R. Only this part contains R. So the variation dl dr is basically dl dr for these two terms. So dl dr, the right hand side of the equation, it comes from that two term, phi and a term. It's basically the spatial derivative of phi and spatial derivative of a. Okay, and this is just standard spatial derivative, so you can write down them as spatial derivative. Okay, so this is the right hand side. And left hand side equals right hand side. Notice that the right hand side, now we have both of them ready. We can write them together. We can combine them together. Okay. Now let's play a trick to rewrite this equation motion a little bit. And the way to rewrite it is to keep dp dt on one side and move everything else to the other side of the equation. Okay, that's what we did here. The same equation, I moved everything to the other side. Okay. And we can write down the same equation for the x component and the y component and the z component. Okay. When I equals to x, we got this equation. When I equals to y, we got this equation. When I equals z, I got this equation. So we have three equations of motion because I have 3 degrees of freedom moving in x, y, z different directions. Okay. So these are my 3 equations of motion. These 3 equations of motion can be combined together in a vector. The left hand side is dp dt. Okay, px, py, pz. Combine them together as a vector p. Okay. The right hand side, this first term, derivative of phi. If we combine these 3 equations together, it gives me the gradient of phi. Okay. And time derivative of a. When we combine these 3 components together, it's a time derivative of vector potential. Okay. Similarly, for the last 2 terms, we got q times derivative of v dot a minus v dot derivative of a. Okay, so the last 2 terms, sorry, the last 2 terms, we can combine these 3 equations into this vector form. Okay. And here, you may notice that this term is a little bit different from the formula we have here. Okay. So this formula is a little bit different from the formula we have here. In the formula we have here, the derivative only goes to a. Velocity is outside my derivative. Okay? Velocity is outside my derivative. We only have derivative to a. But in this form, we have derivative for both v and a, v times a. So it may look like this term and this term is a little bit different, but they are actually the same. Okay? The reason they are the same is because v is velocity. V do not depend on r. So for spatial derivative, v is a constant. For a constant, put it outside or inside derivative doesn't change anything. So this term is exactly the same as this one, and I explained it. Okay. So anyway, this is the equation of motion we have. So this equation of motion, the left-hand side is easy. The right-hand side contains 2 parts. The first part is easy. This guy inside the parentheses is nothing but electric field. Remember, the electric field by definition is this guy. Gradient of scalar field with minus sign minus time derivative of a. That's exactly what we have here. So the first term is nothing but electric field times q. Okay. The second term is a little bit more complicated, but one can prove quite straightforwardly. The second term is actually q times velocity cross b. Okay. To realize this, we need to replace b field with curl of a. We know b is curl of a. Okay. So q times v cross b is actually q times v cross curl of a. Okay. When we have 2 cross products, we can use this identity we learned in vector analysis. Okay. Using this identity, we can rewrite this cross product of cross product in this way. And if we write it down, oh, sorry, there should be a q here. There should be another charge q here. Sorry, I forgot factor of q, I will fix that. If we use this identity to rewrite this formula, we realize immediately this guy equals to 2 terms. These 2 terms are precisely what we have here. Okay. The bottom line, first term is nothing but the QE. Second term is nothing but the QV cross P. Okay. So we find that the momentum, time derivative of momentum, the equation of motion, is this guy. Okay. And by definition, the time variation of momentum, time derivative of momentum, is my force. So this right-hand side of the equation should be my force. And this force is exactly what we learned as Lorentz force. Okay? Electric field gives me a force of Q times E. Magnetic field gives me a force of QV cross P. Okay? That's exactly what we learned before. So for the equation of motion for the momentum, the time variation of momentum equals to the electric and the magnetic force we learned. Okay. Again, I want to emphasize here, in the beginning of this section, we didn't assume any knowledge about E and M. Okay, we didn't assume we have Coulomb's law. We didn't assume any of those physics laws. The only thing we assume is symmetry. Gamma times Lagrangian need to be a scalar. And if we assume that is true, then we automatically get this equation of motion. And this equation of motion automatically tells us the force E and B field give a charged particle should be this. Okay, so this physics law is not extant. As long as we preserve symmetry, it has to be true. Okay, so that's the power of this Lagrangian action approach. Even if we don't know anything about the details about how charged particles move in the E and B field, it will be generated automatically as long as we follow the symmetry. The symmetry will give us a unique answer, and there's no freedom to adjust. The only freedom is the unknown parameter we have. Okay, we don't know the rest mass of the particle. That is something we need to measure experimentally. But aside from that, all the equations of motion, aside from this unknown rest mass we need to measure, everything is fully determined by just looking at this thing. Okay, so that's the equation of motion. Before we dismiss, let me talk one more topic. That is energy. Okay, so we have already get the equation of motion. For energy, and more precisely for the time derivative of energy, we can calculate time derivative of energy in this way. Okay? So time derivative of energy is Hamiltonian. So time derivative of energy is the time derivative of Hamiltonian. And Hamiltonian, we know the energy of particle is this guy. Okay, and the energy of particle is this guy. Okay, this is p squared c squared m0 squared c to the first. And we just need to take time derivative of this object. If we take time derivative of this object, M0 and C don't have T. The only part that contains T is P. Okay, P is the only object that contains time. So at the end of the day, if we do the derivative, all the derivative goes to P, and the derivative is actually this. Okay, so d energy dt is this guy. Okay. And here we use the fact P squared is P dot P. Okay, so this is the time derivative of energy. And once we know the time derivative of energy, notice that there is a dp dt here. Okay, we have dp dt. And what is dp dt? dp dt we just figured out. It's this guy. Okay, dp dt equals this guy. This is my equation of motion. Okay. So I replace dp dt with this Lorentz force. Okay. Replace dp dt with electric force, magnetic force. Okay. And we still have p dot this guy. P dot electric force, p dot magnetic force. Okay. So let's look at this quantity. First of all, this guy is 0. Okay. The reason is because this is a mixed product. V cross B means V cross B, this vector is perpendicular to velocity, but P is parallel to velocity. If I have P parallel to velocity, dot product with another vector perpendicular to velocity, the unit product of two orthogonal vector must be 0. This guy must be 0. Okay, so this term is 0. If this term is 0, the d energy dt contains only one term, that's the p dot e term, which is this guy. Okay, and we can rewrite this formula a little bit. Okay, so if we simplify this formula a little bit, we can find that this coefficient can be simplified dramatically, and the end of the day is just qv dot e. Okay. What's qv dot e? V is velocity, qe is force. It's electric force. Okay. So velocity dot force is power. Okay. The energy dt equals power. This is exactly what we learned in Newton's mechanics. Okay. The energy, variation of energy in time is power. And the power is velocity dot product with force. And we have velocity here, and we dot with the electric part of the force. We don't have velocity dot the magnetic force. And the reason is because velocity is perpendicular to magnetic force. So the magnetic part of the force do not have any power. They do not do any work to my charged particle. Okay? So as far as the charged particle's energy is concerned, only the electric field part of the force gives you work and changes energy. Okay, so that's exactly the same as what we learned in classical EM. Okay, so this is all the topic we want to discuss today. Let me summarize. So in today's lecture, we look at a charged particle moving in a E&M field. At the end of the day, we find we recovered everything we learned in 505. Okay? But I want to emphasize that this knowledge we obtained here, we do not assume any knowledge about 505. The only thing we assume here is symmetry. Okay? It turns out that as long as we assume the proper symmetry, this equation of motion, this energy equals to mass times speed of light squared, all of this naturally comes out as a consequence of symmetry. Okay? So again, I want to emphasize this very amazing result. Okay? So E&M, it looks like a very complicated theory. It involves lots of things. But it turns out that this physics laws, we don't have any freedom to adjust it. It's not just our universe happens to follow this law. Okay? It is our universe has this symmetry. And if our universe has this symmetry, the law of E&M can only take this form. There's just no other way to write it down. As long as we assume we have this symmetry, as long as we assume this E&M field obeys the gauge symmetry, we have gauge choice. Okay, so I think this is a good point to stop. And in the previous part of this chapter, we showed that if we know symmetry, it can tell us a lot about the physics law and the dynamics of E&M and charged particles. In the rest part of this chapter, we'll explore a little bit further about symmetry. Okay, so in the rest part of this chapter, we'll explore the relation between symmetry and the conservation law, and show that every symmetry leads to a conservation law. And from there, we can naturally get the definition of energy for E&M field, momentum and E&M field, etc. Okay, I think this is a good point, and I will stop here, and I will see you next time.